Back when I was a younger, greener, more eager teacher, way back in 1990, I always thought that eventually I would like to move into administration. Because I believed, and I still do, that, if you're just going to sit around and complain about stuff without being willing to do anything about it, that's kind of dumb. These days, I don't really complain. That's just how I get around it. I just close my door and hope the people above me leave me alone. But the longer I started working in academia and the more I started to listen to what administrators say, the less I wanted to sound like that. Because administrators say some really stupid things sometimes. They're not stupid people. I mean, pretty much everybody that works in administration for any college has some graduate level degree. Smart people can say stupid things. Case in point, look at the last 20 episodes of this monstrosity. They just can't call a thing the thing that we've been calling it for years. They've got to come up with new, more creative, better names for it, which makes things more confusing. Pardon me, could you tell me where the library is? Oh, you mean the Academic Resource Center? I guess. Hey, do you guys have a tutoring center? You mean the Student Higher Academic Teaching Services? SHATs? And I know a lot of people who watch these are my students. No, I'm not just talking about our college. I've been to other schools. This is rampant everywhere. But my absolute favorite dumb thing of all time that I've been hearing a lot lately is the phrase learning college. We want our college to be a learning college. Oh, that's good, because those not learning colleges, man, they really suck. I don't even think they get accredited. I mean, seriously, what other industry says that kind of stuff? We want our restaurant to be an eating restaurant. We want our hospital to be a healing hospital. We want this gas station to be a gassing gas station. Oh, I forget that one. We want this church to be a religious church. We want this gym to be an exercise gym. We want this bank to be a money bank. We want this bar to be a drinking bar. We want this whorehouse to be a Percent composition is usually taught right after the mole is introduced and all those gram to mole types of conversions. And it's around the time in General 1 where I like to say the fun begins. And I think because of that, people tend to forget some of the stuff that they knew before ever taking a chemistry class. For example, percent composition is nothing but percent math, part divided by a whole. And don't let the fact that we're using elements and compounds throw you, and all the mole stuff that we talk about. Don't let the chemistry throw you, as I'm very fond of saying, particularly at this point in the semester. For example, butane has the formula C4H10. You have 4 carbons, 10 hydrogens. They add up to a total molar mass of 58.12 grams per mole. So those 4 carbons each weigh 12.01 grams per mole. You divide that part by the total, that gives you a percentage of 82.66%. Because all percent composition is just the mass percent. And we're using molar mass because that's the easiest masses to deal with. So, and you got 10 hydrogens that are 1.008 grams per mole apiece. Divide that part by your total of 58.12. That gives you 17.34% of that total molar mass belonging to hydrogen. And there are actually ways to experimentally determine a compound's percent composition. It's a little technique that most people call elemental analysis. And you guys may do that in a lab later on if you're taking the lab component of this course. And we can take your elemental analysis data, your percent data, and convert that to the formula. It's a way to kind of verify that we have the compound we think we made, or to figure out what compound we're actually making. But when you go backwards from what we just did, compound to percent, here elemental analysis, you're going from percent to formula. The best you can do is the empirical formula, the simplest atom ratio. Because anything with that ratio is going to have the same percent composition. Going back to our butane example, 4 to 10 is, that can be simplified to a 2 to 5 ratio. A compound with the formula C2H5, that also has a percent composition of 82.66 carbon, 17.34% hydrogen. And anything with that 2 to 5 ratio is going to have that percent composition. Because that's how percentages work, if you think about it long enough. So the best we can do going from percentages to formula is the empirical formula. If you want to figure out the actual molecular formula, you need some other information, and we'll talk about that near the end. But no matter what percent composition, what elemental analysis data you're given, you can figure out the empirical formula in the same 3 steps. For example, let's say you have a compound that's 22.56% phosphorus and 77.44% chlorine. First thing you want to do is you want to convert those percentages to masses. And we do that by pretending we have a 100-gram sample. You can use any mass you want. The reason we use 100 grams is really for convenience, because percentages are based on hundreds, percent per 100. So if you have 22% of 100, you have 22. So it gives us 22.56 grams of phosphorus, 77.44 grams of chlorine. So again, you can use any mass you wanted to at this stage, and by the time we get to the 3rd step, you'd come up with the same empirical formula. We're just using 100 for the sake of convenience to make that first step easier. So you can see all we're really doing is converting that percent symbol to a gram symbol. So that's step 1. Step 2, we want to convert our grams to moles using our molar mass conversions that we looked at, again, usually right before we get into this stuff. So if we have 22.56 grams of phosphorus, we can use its molar mass to give us 0.7284 moles of phosphorus. 77.44 grams of chlorine should be 2.184 moles of the element. So finally, now that we have our amounts in moles, we can get our ratio. And the simplest way to figure out our ratio of each element is just to divide everybody by whichever one is the smallest. So in this case, phosphorus has the smallest, 0.7284 moles. Divide it by itself, that gives us 1. We divide 2.184 moles of chlorine by 0.7284. That gives us 0.2998, which is close enough to 3 that we can round up. So that means that our ratio of phosphorus to chlorine is 3 to 1. Put those together, we get a formula of PCl3. So let's do one more to bring up one more point. Let's say you have a compound that's 89.9% carbon and 10.1% hydrogen. The first step is just to pretend you have 100 grams and convert your percentages to grams. Next step, you want to take those grams and convert to moles, giving us 7.49 moles of carbon, 10 moles of hydrogen. Third step, just like before, is to find your ratio by dividing everybody by whichever one is the smallest, which in this case is 7.49. So you divide 7.49 by itself, you get 1 for carbon. 10 divided by 7.49 gives you 1.34 for hydrogen. And some people will want to round up or round down to 1, and that'll give you an empirical formula of CH. But that's not actually the answer here. And again, there's an easy way to check your work. If you find the percent composition of CH, you get about 92% carbon and 7 point something percent hydrogen, which, 2 percentage points may not seem like a lot, but again, if your formula is correct, it should be a little closer to what's given. The mistake here is you rounded too far. And this is because basically the inherent sort of issue with how we're figuring out the formula in the last step. You know, we're dividing everybody by whichever one's the smallest, but that's always going to give us a ratio of something to 1. But not every ratio is something to 1. You can have a 3-to-2 ratio, a 5-to-2 ratio, 7-to-3, 9-to-5. The way you spot that you have one of those other types of ratios is you look at a number like 1.34. That's really close to 1 1/3. So your ratio isn't 1-to-1, it's 1 1/3 to 1. And the way we get rid of that fraction is we divide by whatever the denominator is, which in this case is 3. So dividing both of our subscripts by 3 gives us a 4-to-3 ratio. And in the lecture side of things, you know, when you're doing homework problems or practice problems, it's really clear, usually anyway, unless your teacher's throwing you a curveball. When you have a number that you can round, like before we had something 0.99, that's, you can round that up. If you have something 0.0 something, you can round down. But if it's not that close, then be on the lookout for fractions. Again, 0.33 is a third, 0.5 is a half, 0.25 is a quarter, stuff like that. Get tangled up here, sorry. So again, you don't want to round those away. Right? You want to get rid of the fraction by multiplying whatever's on the denominator. Yeah. If the denominator is a 3, so a third, you multiply by 3. If it's a quarter, you multiply by 4, etc. etc. And you know, if you check your work here, again, you're going to get the proper percent breakdown. Although I didn't do it on the screen. I didn't, did I? Nope, didn't. But again, except for that one little thing, it's the same 3 steps. You know, percent to grams, grams to moles, moles to your ratio. Just when you're in that 3rd step, watch out for a fraction. Although again, if it isn't really close to a whole number, that's a clue that you probably got a fraction. At least in a lecture. In real life, you know, when you're doing this in a lab setting, you might get things like 0.83 and you got to decide whether you're going to round or if that's close to 3/4. But yeah, we try to avoid too much real world stuff in lecture. I do anyway. All right, anyway. Back to what I said earlier about this being the empirical formula. If you want to know the molecular formula, you need to know that compound's actual molecular weight, or molar mass, whatever you want to call it. And kind of like, you know, elemental analysis is a common way to figure out percent composition, there are really common ways to experimentally determine a compound's actual molecular weight. Again, you might do it in a lab at some point this semester. So, for example, the problem we just did, the empirical formula was C3H4. Let's say that we also know that the molar mass of the compound is 160.2 grams per mole. So first thing you do is you figure out the molar mass of your empirical formula. Those 3 carbons, 4 hydrogens, that adds up to a total molar mass of 40.06. Next, you want to divide the actual molar mass by the empirical formula's molar mass. So you divide 160 by 40, you're going to get about 4. So if your molar mass, the actual molar mass, is 4 times higher than the empirical formulas, that means the molecular formula for the compound, the actual formula, is also 4 times higher. So you take those 3 carbons, 4 hydrogens, multiply them to give you a formula of C12H16. And again, there's a really easy way to check your work. If that's the actual molecular formula, those carbons and hydrogens should add up to whatever molar mass was given. And in this case, they do. Now let's go back and look at our first example where the empirical formula was given as PCl3. And let's say the actual molar mass was 137.3 grams per mole. Well, you add those 3 chlorines and that 1 phosphorus together, you already get 137.3. And that'll throw students at first. But again, that just means that the empirical formula and the molecular formula is the same thing, which there's nothing wrong with that. When you think about water, H2O, all right, 2 to 1, that's the simplest ratio. Sometimes the molecular formula is the simplest ratio. So again, don't let that throw you. Again, don't let simple stuff throw you because you're starting to be introduced to things like moles and other chemical stuff. Don't let the chemistry throw you. As I say again and again and again. But repetition can be good. Sometimes. Maybe. I don't know. But we'll talk about more stuff at another time. I'll see you folks later. Bye. Whew. Anybody else smell toast?